Everybody, welcome back to our next topic in grade 12 physics. I want to start off by saying having a little bit of issue with my microphone today, so the audio might be a little, well, not quite as good as we're used to, but hopefully it's okay. I hope to have the problems resolved soon. But anyways, what we want to talk about today are the idea of electric fields. So we have talked about gravitational fields, how those sort of work and why they're important, and we've also talked about electric force and how that comes about. So we want to now kind of combine those two ideas and look at this idea of, again, an electric field. And so let's start our discussion today with a quick review of gravitational fields. And so if you remember what a gravitational field is, it's this sort of, well, a field that an object creates in the space around it. And it's going to cause objects that are close to it to experience a force. So for instance, if we look at the Earth here, the Earth would have a gravitational field around it, causing any massive objects near it to be attracted to it. The field lines represent the direction of force this isolated mass would experience. And so for instance, if I put an object right here, where the red dot is, it would feel a force pulling it in towards the Earth. Or if I have an object, let's say, traveling in like this, any point along here, it's going to feel a force in the direction. So the path of this object would actually be somewhat kind of curved, not quite that much. It'd be probably more along this sort of path here. And remember, in our diagram here, the closer the field lines are together, the stronger the field. And we can actually measure this or report this gravitational field strength by using the vector g. So there's, again, our quick sort of recall of what a gravitational field is. So electric fields are, again, the same sort of idea, but the only difference, of course, is now we're dealing with charges as opposed to masses. So we're going to be talking about an isolated charge as opposed to an isolated mass. So which sort of direction and magnitude force a charge would experience a force. But the difference here is that electric forces are attractive or repulsive as opposed to just attractive, which is gravitational. So we have to then decide on a direction to be positive or a charge to be positive. It certainly is an arbitrary choice, as I talked about last time, but by convention, the field is drawn to indicate the direction of force an isolated positive charge would feel a force. So for instance, if we have a positive object creating the field, and I put a test charge here, let's say here's my test charge, and if it were positive, it would feel a force this way. So again, the arrows represent the direction a positive test charge would experience a force. And similarly, if I'm over here and I put my positive test charge here, it would experience a force, of course, towards the negative charge. And so you can see the shape of this field is very similar to the shape of the field we expected from before, because again, the equation for the force, or the expression for the force for electric force, is very similar to the gravitational force. Okay, so let's try and now quantify this electric field. And the way we're going to do this is using this thing called the electric field vector. It's given this symbol here. This symbol kind of looks like an E. It's the Greek letter epsilon. I don't know if you've seen that one before, but it's kind of like a curly E, and it's a vector. And what it actually is, it's the strength of the electric field. And the way we define this is by the force that an isolated charge would experience, the force that a charge would be there per unit charge. So if you imagine you have an object, you measure its charge, you measure the force it experiences, and then just divide by the charge. And so we call that electric field vector. Its units are going to be newtons per coulomb. So again, if I have an object, it might have an electric field of 10 newtons per coulomb. What that means is every coulomb of charge I put there, there would be a force of 10 newtons. And since we know our expression for the electric force, like we talked about last time, we can actually then simplify this and just cancel out the little q when I divide this whole thing by little q. And there's our expression for epsilon. And just briefly here, you might notice that I've been using a capital Q here as opposed to a little q. It really doesn't matter. I'm just using it to denote the fact that we're dealing with a single, usually large charge. And this is the charge that's in question here, not the unit positive charge of the test charge. This is the charge of the object. So we'd be talking about the electric field from charge Q, capital Q, right here in this case. So for instance, epsilon would be the electric field from charge capital Q. All right, great. So let's then compare this to something you're a little more familiar with. So you're probably a little more familiar with gravitational fields. So if you take a look at how these things compare, well, let's start with just simple pictures here. So here is a giant mass, the Earth, and here is a charge. And if you notice, the shape of the fields are very similar. They're all sort of pointing at a single point, the center of the object. They all sort of radiate out, they're radial. The only difference here, again, maybe I should have had a negative charge here, but it's not a big deal, is that the electric field can be attractive or repulsive, and gravitational field is always attractive. And actually, the expressions for the fields, so the electric field given by kq over r squared, and the gravitational field given by gm over r squared, look very similar. Because again, their forces behave in very similar ways. So that's a kind of nice analog for us here. So we actually have a lot of similarities between these two things. So let's actually do a numerical example here. So let's calculate the electric field from a point charge. So let's pretend we have a negative 1.4 millicoulomb point charge. So again, little m means milli. And we're at a distance of 2.4 meters from it, and we happen to be east of it. So if I were to draw a picture here, there is our charge. Minus 1, well, let me try that again. Minus 1.4 millicoulombs. And of course, we know the electric field radiates out in all directions. Kind of like this. And since it's a negative charge, we know that a positive charge would experience a force towards it. And for this particular question, I want to imagine that I'm in position over here. And again, we should probably have a compass rose here. And I want to know what is the electric field right here. So of course, we're going to go through it and use our epsilon value. Again, make sure you're using SI units here. Okay, and again, you plunk this stuff into your calculator, you do some calculations, and end up with an answer of what I'm getting. This. And so let's just pause and think about what does this actually represent. So just like we had before, again, we have a negative sign here. What that means is that this object, or I guess if I put a test charge here, we'd actually be having this object be traveling towards it because it's a positive test charge. And so we have a strength of 2.19 newtons per coulomb. So what that means is every coulomb I would put at this distance, at this location, would feel an attractive force of 2.19 by 10 to the 6 coulombs, or 2.19 mega, or let me try that one more time, sorry. So every time I'd put, let's say, a coulomb right here, it would experience a force of 2.19 by 10 to the 6 newtons, or you can also go that 2.19 by 10 to the, 2.19 meganewtons, and that would be an attractive force. We know that again because the electric field vector is pointing towards it. The other way we can say is because, well, it's a negative, and a negative is going to attract a positive. All sorts of ways we can say the same thing in this case. And just something else I can kind of draw your attention to here that's kind of neat is that, of course, electric fields, just like gravitational fields, actually work in 3 dimensions. And so what I have here I think it should, yep, that should work pretty nicely for us here. We have a charge here, and what I've got is actually all sorts of different field lines coming off in 3 dimensions. Now, it's probably pretty hard to see it at first, so let's just show it in 2 dimensions to begin with. So here are the field lines coming off. In this particular program, the brighter or the more white the lines, the stronger the field, and the green denotes the weaker lines, or the weaker field. And so you can see it's coming off in this radial direction like we expect. But if I then switch to, let's say, the other plane, you can see again it's that same shape. So I do it in all the directions and it comes off in all sorts of directions radially. And if I instead show you as the vectors and they're all pointing towards it, you should be able to tell me the sign of this charge. And that's actually going to be one of the questions I'm going to have you answer on that form at the end of the video here. So the first question will be, what is the sign of this charge? So I'll ask you to tell me that one. But one of the neat things we can actually do is look at some different options here. So if I take a look at something again called a dipole, actually let's look at a double point charge to begin with. And I'll go back to our field lines. What we're actually seeing is two similar charges and the field around them. And again, I think this is kind of neat. So field lines can actually add up together. They can actually work together. So just like we could with gravitational fields, there's going to be a superposition or an addition of these fields. So these 2 points would both be producing a field in the space around it, and the sum of the field would actually be the total field in space. And I can actually move these charges closer together, and we can see the effect on the field, or I can move them further apart. But one of the neat things, if I bring these two things really close together, and I put them so close together, it's like that they're a single charge, and that should make sense, because if we get far enough away from this, that we really don't care how separated they are as long as we're sufficiently far away. Another way to say that is, even though the particles in your body are made of positives and negatives, you don't really feel the electrostatic attraction or repulsion unless there's extras, because even though the electrons might be momentarily closer to you than the protons, there's so much, the separation between the two types are so small that they might as well be on top of each other. But of course, if we make that separation larger, then we certainly have an effect on the field. Another thing that's kind of neat is if we look at something called a dipole, and that's where these two charges are opposite, we get a pretty cool looking shape. So we look at, again, some different sort of slices, they call them, so just the two-dimensional representation. So there's in the x direction. And if I look at just the y sort of plane, you get this kind of cool shape here. This should look very similar to magnetic fields you probably looked at in grade 11. And I think the z slice should be, rotates like this, again, magnetic fields, but I can actually then also slide this up and down, and you can see how that field changes and how the strength of those lines change as you move further and further away. And again, just like before, one of the neat things we can talk about is if these get close enough together, bring it really close together, so a positive and negative charge really close together, if I put them almost on top of each other, there is no electric field because they are so close together for each other, just like, again, those positives and negatives. So I think that's kind of neat. All right, so there's that idea there. Awesome. So let's go back to our idea here and summarize just sort of what we just did. This idea, there's multiple sources that gravitational electric fields can add together and interact to form other fields. And so again, just like we talked about, or I talked about there, that look at how the field looks like in between, but as you go far away, you're actually getting then this behavior that looks like it's a single point charge, which again I think is pretty neat. So I think that's all I really wanted to cover today. So I hope that makes sense for you. So again, there'll be a couple questions for you to answer on the Google form this time. The first one being, again, I'll remind you, I'll go back to our first one, which was just a point charge. And I showed you the force vectors. Oh, not force particles. There we go. I wanted to know what was the sign of this charge here. Positive, negative, neutral, I don't know, whatever the heck options you come up with there. So what is that charge? And there'll be a couple other ones there. So I hope that makes sense and everybody understands what's going on. And I'll see everybody in class tomorrow. Have a good night.